Hello, everyone, and thank you for joining us. Today, we'd like to talk about continuous profiling in production with eBPF. Before getting started, we'd like to acknowledge how much we've been able to lean on other open source contributions. Our short list of highly impactful underlying projects includes eBPF, BCC, and flame graphs. So today, we'd like to first get you into our headspace and talk about what the problem, what we were trying to solve and what the problem was, and then get into the technical details about the underlying architecture of how we solve it, briefly show you a demo of this in practice and action, and then we will surface a few of the technical challenges that we overcame along the way. So this story begins when we needed to profile our own application. We were actually using the profiler included with BCC. It's an eBPF-based profiler. It gave us great power in that we did not need to recompile our application or redeploy our application, but there was still a high amount of friction between maybe wanting a stack trace and the jumping through the necessary hoops to go and look at it. You would have to log on to a node in the cluster, turn the profiler on and off, get the data down, render it as a flame graph. So our vision here, after experiencing this, our vision was to have an instantly available profiler that was, at the bottom line, no hassle. And this is now built into Pixie, which as an architecture, you have installed on the nodes in your production cluster what we call a Pixie Edge module, or PIM. And the PIM is fundamentally a set of eBPF probes that collect data, maybe data about HTTP request latencies are relevant to our topic today. The BPF probe would collect stack traces, and these stack traces and data sit in the PIM. But if the Pixie cloud, which is a perhaps on a separate cluster or your same cluster, needs to run a query, it gets the data off the PIM, aggregates it, and renders it in some certain way that is going to show in your web browser. So in our case, your web browser would initiate this whole thing, and the Pixie cloud would get data from the PIMs, and you would just see a flame graph of everything across your entire cluster. So right now, let's quickly take a look at that in action. What I show you right now is my Chrome web browser communicating with a self-hosted open source Pixie cloud, which is running on a fresh Google Kubernetes engine instance. And then there's some more stuff on the cluster. For example, this online boutique toy application. And maybe we're interested in debugging the server front end portion of this, and we can look at these stack traces, zoom in a little bit, and maybe we notice there's a syscall here taking up some CPU time, and that might just be surprising, might be a clue about what you need to optimize. So in the interest of time, let's get back to our technical challenges and describe a little bit about what we found. And at the outset, we knew that the BPF piece of this, the probe itself, was very efficient. The cost of just getting one stack trace sample is about 3,500 CPU instructions. And you don't need to sample these at a very high rate. We chose 91 Hertz or every 11 milliseconds. And when you put that together, that should be less than 0.1% CPU overhead. But as we built this, what we found is there are other overheads that can cost you. And some of these are BPF or BCC related. And we would just like to refer you to our blog post where we describe how we reduce these other related overheads by about 4x. And in summary, we'd like to once again say we are now an open source CNCF sandbox project. Please check us out. You can clone the repo from GitHub. You can get your eyeballs on it and send us feedback or suggestions. And in fact, we would welcome some contributions or any directions or new directions and ideas. And with that, we'd like to say thank you. Thank you for listening.